Hello and welcome to Physics Problems One by One. So here is a problem. As always, read it, maybe once, maybe twice, and then pause the video and try to solve it yourself. So before going down and diving into all these complex problems, friction, inclined blocks, pendulums, everything, I want to put an emphasis on the difference between mass and weight. We already talked about mass, we talked about weight a lot, but let's specifically talk about the difference between mass and weight. So first of all, mass. F equal ma. And this basically definition of the mass. Mass is a proportionality constant, a constant of proportionality, if you wish. Constant of variation, they say. But basically, it has two variables, F and A. They change, but they change proportionally. You increase F twice, acceleration increases twice. You increase F 3 times, and acceleration increases 3 times. And this thing is simply a proportionality coefficient between those two. And this is, as I said already, Newton, his genius, who was able to deduce or suggest or invent this formula, F equal ma. And yes, I mentioned that F is a cause of acceleration. Until you put any force, there is no acceleration. Acceleration cannot come from nowhere and create a force. Never happens. It always two body communicating with another, interacting with another. One body pushes another, creates a force F, and boom, as a result, acceleration is created. And this formula tells that if the same force applied to a massive body, to a big body, acceleration becomes very small. If the same force applied to the light body, m is small, light body, no mass, acceleration becomes very big. What this formula hides is that F is primary and F causes acceleration. You can say, oh, I know acceleration, that means I know A. Acceleration causes the force. No, the force causes acceleration. For such, it would be actually more logical to write this as this. And then this would be the coefficient, but how you will call it? This is mass. The bigger the mass, more massive is the body. How you call this? Lightness. So you will call it, for example, lightness. So massive body, m is big, it's very light, okay? So, but then what it says, if I have F and I push apply it to the light body, acceleration becomes very big. But if lightness is bigger than acceleration, but lightness, it's like double negation. And it's becoming very confusing. So probably that's the reason why historically they say with something that we are very comfortable as humans. Mass, massiveness, the size of the body is kind of in our subconsciousness. The massive body, the same force, small acceleration. Light body, m becomes small, acceleration becomes big, and we push with the same force and it goes. Try to push the house, it will not go. Try to push, I don't know, the cart, it will go very fast because house is very big mass, and or truck or train has a very big mass, and the cart has a very small mass. So this is exchange, trade-off between m and a. Multiplication is the same force. So okay, so mass is a property of the body, and it doesn't matter where this body is located. Here, on the moon, in the middle of the earth, if you ever will be able to go there, on the orbit, anywhere, on equator or the North Pole, it's the same. Mass is a property of the body. And it would be very different with weight. That's why I will emphasize later the difference. But for the time being, mass is a property of the body. But then comes the question how you measure mass. Because in physics, everything is about measurement at the end of the day. So how you measure mass if that's all you have? Well, the way would be to measure force, measure acceleration, divide one over another, and F over A, and you receive mass. And you do this in different situations with different forces, measuring different acceleration for the same body. And you will have M1, M2, M3, and basically then you can put a graph and table, but M should be always the same, like within the error of measurement of A and measurement of A. But how you measure F? Well, F is possible to measure with the spring scales. This is a spring, and if you put a force here, the spring would become a little bit longer. And this would be the difference, delta, and the result, the spring would like to go up, and it would be the force F. Or vice versa, you can put upside down, this is a ground, this is a spring, this is a platform, and you apply some force, and then it will be compressed. And this will be compressed, and this will create some force, right? Again, the force in both cases is directed up because it won't come to this equilibrium point. But again, this delta would be proportional to F. So delta would be equal kF, and K is a property of the spring. So yeah, they knew how to measure force 400 years ago, but then how you measure acceleration, it's very difficult really, because you have to measure distances, you have to measure speeds, you have to measure time, and it would be confusing. And also how you create the situation when there is only one force applied to the body. In real life, it's never a situation, it's very difficult to create this situation when only one single force is applied to the body. We can do something like we can put the body on the flat surface, it would be a brick, we can pull it with F, and we pull this F with this spring, and we measure this spring is attached to the body, and we measure F, and we say here's a force, and here's a force, and there are three forces, and along this axis, F and acceleration, so this is only one projection, and yeah, we can kind of do it, but still again, measure F is relatively easy, but measure A is relatively consuming. So this direct method is not very easy to do. But fortunately, not always you have to measure using direct method. You always can, for example, you can find the oscillation. This is a spring, you pull the spring out, and it starts to oscillate in this direction. This is the wall, and this is the body. You pull it out, and it starts to oscillate. You can measure time, and this time relates to m. But we don't know this, and to prove me this now would be impossible for you. You have to know differential equations and everything. But this is called non-direct method. And non-direct method in physics are very useful, very useful. And so, they come to this solution just simply a scale. Put this spring, this is the ground, put the body acts down, one force on the body is mg, which is gravity, nothing else, mg applied to the body is gravity, and another is n. And this n is from this spring, and we know that if everything balanced, n equal mg, and we kinda can measure n, we know it, because this is like calibration of the spring as much as how far the platform moves down, and we can measure it, so we know n, and then we divide mg and we get m. And this is perfect way of determining the mass. But humans and everything, we know n already. So we already know mg. Who needs m specifically? Only physicists when they analyze this. But in real life, m or mg, what's the difference? So they call this thing weight, and they call this as mg. So you know weight, you know mg, and implicitly you know the mass. But it's very different. Weight is not even a force. Weight is simply a multiplication m by g. Of course it has the same unit as force, but very important is how we measure weight. We measure weight with this, or we can put this spring, put this down, this would be mg, the force would be returning force n, and again n equal mg, and we know the weight of the body. The important thing, again, only for principal scientific and mechanical and questions, but not in your real life, that this has to be measured stable scale, no acceleration, everything on the surface of the earth. And then, yeah, weight equal mg, and this is absolutely correct. Weight equal mg. But we talked about this in previous installations, that if this is in the elevator and elevator accelerating, that this becomes invalid. So you have to be very careful about how you measure weight. You measure weight in stable system, no acceleration whatsoever, everything is balanced. It happens that gravity force balances n, and that n is the force from this spring, and then you say, oh, I'll call this spring, this force, normal reaction, I'll call it the same like combination, multiplication and mmg, and I call m multiplied by g is the weight. See how I am avoiding to call this thing weight, or I avoiding to call this thing weight. This is easy. mg is a real force, is gravity, but this is the reaction, and then from nowhere comes the weight, which is not the force, nothing, it's just mass multiplied by g. And remember I talked that if everything is moving up and down with acceleration, this becomes invalid, because actually m minus mg equal ma, and m may be equal ma plus mg, or it may be plus minus depending on where acceleration is directed. You have to rewatch those clips, I'm not going there. But what I'm trying to say is that in those systems you try measuring this, you will have different weight. But it's not a weight, it's just the number that this spring scale is showing to you. So spring scale will show a bigger number than your weight, which is combination of m multiplied by g and weight, and it will show exactly this number m by g if you measure it without acceleration. But for us humans, this is kind of acceleration. As this is kind of weight and mass, it's all the same, regular job, weight, mass was the difference, and this is what I'm trying to be very specific here and dedicate the whole clip. Mass is proportionality constant. Constant, proportionality constant, nothing more. And this is immutable property of the body. The body, this body has this mass, and that body has that mass. And yes, this property governs this equation and many other consequences. Weight is completely different. Weight originated from the way of measuring mass. So we started measuring mass with a scale 400 years ago, and we came to very good results and very good methods how to measure this force with a lot of precision and repetition, and all the condition it is the same. And then when we learn how to do it, we don't say, oh, this n equal mg, or let's call and mg, let's give a special name to this mg multiplication. That's it. But sometimes we do another logical step. We say, oh, weight is this force. because you go to grocery store, they put on the scale is electronical of course, but the same principle applies. They put it on the scale shows this is the weight, oh this is the weight, that's how much the potato bag has a mass. In the end of the day you buying mass of potato. But they say this mass of potato will weight such and such, meaning that m multiplied by g is its weight, it's its number. And that's it for today, for this clip. And the next clip I will be talking about weightlessness. Also a little bit related to this, because if weight is mg, how it may be weightless? Well, there is another gap in words that I want to cover. For now, like, subscribe, bell, question, and comment, and I see you next time. Thank you.